Hey, welcome back. I'm going to do another type of example of word problems or related rates questions in calculus. Here we have a question about a blue car that's moving and a red car that's moving. So there's some intersection that they're moving in the vicinity of. One of them is moving north, one of them is moving east, and it's asking for the rate of change of the distance between the cars. It's very hard to make sense of these questions without drawing a picture and reading very carefully the paragraph and seeing how you can use a paragraph to make an accurate picture. And by accurate, I don't mean being able to draw a good car, I just mean being able to draw what's where, so you can relate the positions of things to each other. I'm going to start by drawing the intersection. I got something going north of it, I got something going east of it, and it doesn't matter if you don't know your norths and your easts. But you should know that they're 90 degrees to each other, but knowing that north is like up like this and east is like that, if you got it screwed up, you got it wrong, it would not change your calculus answer. Just change your picture a little bit, but it doesn't matter. Okay, so there's the intersection. Now I'm going to draw a blue car 4 meters north. And I'm not even going to try very hard to draw the car. There's the blue car with blue wheels. It's so blue, it's even the wheels are blue. And let's see. I'm going to label that side. I'll give it a name. I'll call it H. Why not? And at this instant, H is 4. So the blue car is 4 meters north from a road intersection and is moving north with a speed of 30 meters per second. So we gotta think about what that means. The distance between the intersection and the car is h. The car is moving away from the intersection at a speed of 30 meters per second. What's happening is h prime is getting larger. That's telling you the rate of change of the distance between the car and the intersection. So h prime is equal to 30. Positive, not because it's moving north. Don't make that mistake. It's positive because the distance is getting larger, not because it's going north. If it was going south and it was moving away from the intersection, h prime would still be positive 30. And this causes enormous problems in physics classes. I'm glad this is a math class. Less of an issue here. Let's keep reading. There's a red car 3 meters east. So I'm going to put as much effort into drawing that car as I did with the first one. There's the red car. And I'll label that side. I'll give it another name. Let's see. Let's give it a name L. Why not? It's currently 3. L is equal to 3. And it's driving east, so it's driving away from the intersection. That means the distance between the car and the intersection is increasing. So L prime is going to be positive at a speed of 20. So L prime is 20. What is the rate of change of the distance between the cars? Now we've got to take a pause. What does that mean, the distance between the cars? Well, that means, do I have it here today? Do I have my measuring tape? I think I do. Today I do have a measuring tape. Just luck, not by design. I wasn't planning to have a measuring tape. So it's this. This is the distance. You take this end, you give it to the blue car. You take the other end, you give it to the red car. It's that distance. So how would you draw that? Well, you draw that like a straight line that connects the cars. And I may have run out of... No, I have. That is the measuring tape distance between the vehicles. I'm going to give it a name, not being very creative. I'm going to call it D for distance. Okay. So that's kind of step one, setting up the picture, extracting information from the paragraph. And now we have to figure out how we're going to answer this question. How do we find the rate of change of the distance between the cars when I don't have an expression for the distance itself? We got to go back to this. HLD, and we have to make one modeling assumption inside. Actually, a few modeling assumptions. We've got to assume the ground's flat, so there's no hills. We've got to assume that the intersection meets at 90 degrees and the roads are straight. With those assumptions, we can say this is a 90-degree angle. So this is a mathematical model. This is not reality. This is not perfection. But if we don't make these assumptions, there's nothing that we can do. Like maybe it's 89 degrees. We're making the 90-degree assumption that says north versus east, and those are 90 degrees to each other, so we're going to go with it. Now what? What does that look like? You've seen this before. I don't know what grade you saw it last, but you would have seen it first time probably in grade 9 and grade 10. It's Pythagorean theorem. How do you relate the sides of a right angle triangle to each other? Well, the hypotenuse, in this case, it's always the side opposite the right angle, but in this case it's called d. D squared is equal to h squared plus l squared, Pythagorean theorem. And we're going to have to use this expression in two different places. Let's use it in the first place. We want d prime. So d squared is equal to h squared plus l squared. We can take the derivative of all the pieces using implicit differentiation. We get 2 times d prime equals 2 times h prime plus 2 times L prime, since each are functions of time. We can isolate for d prime. I'm going to do that in 2 steps. 2d prime is equal to, when the common factor of 2 out, I get h prime plus L prime. Now we can cancel the 2's left and right. And then divide both sides by d, and I get d prime is equal to h prime plus L prime all over d. We can start something in data that when we find that we get stuck. We have h and h prime. We have L and we have L prime. So I'll plug those in for L prime. Oh, I screwed that up, didn't I? Gotta be careful. H times h prime, so 4 times 30. I was thinking of something else. And then 3 times 20. We don't have d. We're gonna have to find it. So I haven't used purple yet. No, not really. So let's find what d is at this instant. At this instant, d squared is equal to h squared plus L squared. So I'll plug that data in. 4 squared plus 3 squared. You'll see this combination numbers come up a lot because it's nice. 16 plus 9. So d squared is equal to 25. We get d is equal to plus or minus 5. But remember, it's this distance, and there ain't no negatives on my tape. There's no negative distance between the cars, so throw the negative away. Only positive 5, since distance. So that'll go underneath inside the expression over 5. Now let's simplify. 120 plus 60 over 5. 180 divided by 5. $36. So I'll give you a little bit of a hack for division by 5. Divide by 10 and then multiply by 2, especially if the number ends in a 0. Because multiplying by 10 and dividing by 10 and multiplying by 2 is the same as dividing by 5. Just a little bit easier to think about. It's like a hack. That's it. So even though one car is moving 30 kilometers an hour, the other car is moving 20 kilometers an hour, or whatever, the meters per second rather, the distance between them is increasing at 36 meters per second. It's like a combined effect of both movements. All right, and this next one is a classic. It's probably the most common example in side-related rates. It is the ladder sliding down a wall. I think you can find it everywhere. Every textbook, anyone who has math videos does this example. So I'm going to draw a wall. I'm going to draw a floor, since this is a room. And then I'm going to draw a ladder. It says that the ladder is 5 meters long, so I'm going to start labeling these sides. I'm going to say that this side is, see, it's arbitrary, right? I can use L if I want, for the ladder. I can use D, because I used D in the last one for the hypotenuse of a triangle. It's up to you. I'll pick L, give it a name. All right. The base of the ladder, that's the name for the bottom of the ladder, is 3 meters away from the wall. So I'm going to give this name a measurement. I'm going to call this B for base. So at this instant, B is equal to 3. Oh, I should label L is equal to 5. B is equal to 3, and is sliding away from the wall at a rate of 8 meters per second. So if it's sliding away from the wall, that means the distance between the wall and the base is increasing. So it's an increasing rate of change. That means B prime is positive 8. Then it says, find the rate of change of the distance from the top of the ladder to the floor directly below. So that there is the top of the ladder. I'm going to call this distance from there to there, I'll call that T for top distance to top of ladder. And I should label this here distance B. Okay. So at this instant, we don't know what T is. T equals question mark. And what do we want? Find the rate of change of the distance from the top of the ladder to the floor directly below. We want T prime. I want you to think about this logically before you start doing calculus. If you take the bottom of that ladder, and that ladder is still leaning against the wall when you're doing this, and you pull that base of the ladder away from the wall, like this way, pull along the floor in this direction, what's the top of the ladder going to do? It's going to slide down, right? It's going to slide down as you pull the ladder out. Imagine someone's up here painting, and you pull the ladder out from underneath, they're going to fall. And it's not because of the weights on them, that's not the only reason. It's also going to fall just because the ladder's not getting any longer as you pull the bottom out. It's going to stay the same length, right? So it's got to go down. Just in order to stay the same length as you move the base to the right, the top has to move down. Otherwise, that ladder has to stretch, and it's not going to stretch because it's a ladder. By the way, that's a hint. That's a piece of information that we need to assume. So as we proceed, let's think about our Pythagorean theorem again. We're going to assume that the house was constructed properly and that meets at close enough to 90 degrees that we can call it 90 degrees. So I'll write down that model is from Pythagorean theorem. We have L squared is equal to T squared plus B squared. And notice that the inputs, the locations of the inputs in the model, they're not the same for every question. I have my L along the bottom here. I have my L along the hypotenuse here. Don't fall into the trap of thinking that your labels have to match in all the cases. What makes the equation work is that the hypotenuse, the side opposite 90-degree angle, is on its own. So hypotenuse squared equals the sum of the square of the other two sides. Okay, we kind of already know how this goes. We know we're going to take the derivative, rearrange maybe, plug in some numbers. We'll see what happens. So we'll take the derivative d by dt of both sides implicitly. We get 2l l prime is equal to 2t t prime plus 2b b prime. And we want t prime, so we've got to rearrange for it. But before we do that, I'm going to common factor 2 out from the right so that we can cancel properly. Cancel the 2's. So we have L prime is equal to T prime plus B prime. Then I want to get T prime all by itself. That's the thing that we're after. So I have some rearranging to do. So L prime minus B prime is equal to T prime, just subtracting b prime from both sides. Now I'm going to divide both sides by t. So t prime is equal to L prime minus b prime all over t. Then we'll plug in that data. We have L prime, we have B prime, and we'll have all divided by t. And then we'll simplify. Okay, so the data that we have B and B prime, 3 and 8. We have L, which is 5. And we are missing data. We're missing L prime, and we're missing T. It's easy to find T. Find T at this instant. So L squared, 5 squared plus T squared is 5 squared equals T squared plus B squared, so plus 3 squared. 25 minus 9 is equal to T squared. So 16 is equal to T squared, and that means that T is equal to 4. Not minus 4, because this is a distance between the top of the ladder and the floor. And hopefully we want an answer that makes sense. So I'm going to put a 4 down here for T. Now we have one more hidden piece of information. What's L prime? And it isn't that hidden. L equals length of ladder. L prime equals rate of change of length of ladder, which is 0. The ladder's length doesn't change during this experiment or during this journey, during this process. It's a constant length ladder, so times 0. Let's plug in the information. So we have negative, I'll do it in steps, 0 minus 24 over 4. We have negative 6 as our answer. It's good that the answer is negative because that matches with our intuition. The distance between the top of the ladder and the floor is decreasing. The top of the ladder is going down. It's getting closer to the floor as the bottom of the ladder is pushed to the right. And we'll do some more examples in the next video.